Morning, everybody. We got a lot to do today. But before we get started, so I'm going to do a couple of examples for buoyancy, Archimedes principle, and then we got transition from fluid statics, which is what buoyancy is, into fluid dynamics, and show you some examples for that. And that'll be the end of chapter 14. Before we get there, though, I posted the topics for the exam that's coming up next week. So those are up on Canvas. I don't think there's anything else I'm supposed to tell you. So we will jump right in. Cruel thing to do at 8 o'clock in the morning, I know, but you know. It's the situation we find ourselves in. So we have this object, and it weighs differently in this fluid than it would otherwise. Why does it weigh less? Buoyancy, right? I mean, it's surrounded by a fluid, and so can you tell me, kind of just by looking at the problem, what the buoyant force is? Can you tell me the number? Not 700. It's 100. How'd you figure that out? It lost 100 newtons, right? Now, did its mass change? No. Did big G suddenly change? The universal constant? Oh, right? Little g didn't change. So that weight that disappeared had to come from the fact that now the weight of this object is being supported by this mystery fluid with a specific gravity of 0.7, right? One of the things that is not really clear in fluids stems kind of from, I think, an old-fashioned-ish idea about how you're supposed to weigh things. So whenever it says something weighs 300 newtons in air, and then when it's immersed in a fluid, it weighs something else, the picture that's in the mind of a physicist is you have this object, and it's being held by like a thread or something, and then it's attached to a scale. We saw the video yesterday where they have that scale, right? And I don't know if you've seen these. Sometimes they're in markets and supermarkets and things like that, where the thing you're weighing doesn't like push down on the scale. Instead, it pulls down on the scale from below. So when we're talking about the weight of this object, it's okay to kind of picture. I mean, if you put this. If this were on like a regular bathroom scale or a kitchen scale or something like that, the object wouldn't be suspended in the liquid, would it? It'd be resting on the bottom, certainly if it's more dense than the liquid, right? It'd be resting on the bottom. So there'd be a normal force holding it up. That normal force would be the same as, say, maybe this tension that's holding it up and having it suspended in water. But generally, if I encountered a problem like this, and there's no picture, my first assumption would be that somehow this object is being hung in the fluid, isn't necessarily sitting on the bottom of its container. And I know that can be real confusing, and again, I think that's one of those things that physicists have let sort of slip in, that we're not careful about saying, well, our assumption is that it's kind of doing this. I mean, unless you're told otherwise, right? Sometimes they show you a picture. Or they say an object is put on a spring scale, right? And then they tell you that it's resting on the bottom of the container. Otherwise, you kind of have to assume that this object is floating in the water. So if I want to draw a free body diagram of that object, then what forces are pushing or pulling on it? What do we got? Gravity. We've got gravity. We've had other people pointing up. There's the tension, right? This thing is suspended. Without that rope, without that string, it would sink to the bottom of the container. And then there's one more uppy force. The buoyant force, okay? So that's while it's in the fluid. When it's in the air, what does it look like? What would the free body diagram for that one look like? Still have the gravity, and then basically we don't have a buoyant force when it's in the air. Is that technically true? there a buoyant force acting on you right now? Yeah, you're surrounded by a fluid, you're surrounded by air. And there is a buoyant force acting on you. It's just so tiny compared to, say, the buoyant force that would be acting on you if you were in water, that we tend to ignore that buoyant force when objects are weighed in air. We're talking less than 1/50th of 1% air by taking it into account. All right, so there's our two free body diagrams. Kind of looking at it, we can see the only difference is that buoyant force. And since mg isn't changing and the tension over here in the fluid is 200, and the tension, and the tension in air is 300, then maybe we can see that buoyant force comes directly from that difference. So I know what my buoyant force is. And now we've got to go and find out what they want us to know. We want to know the volume and density of this mystery object. Does the buoyant force have anything to do with density and volume? They're related. How are they related?
Like ratios?
No, by definition. What is the buoyant force? Okay, rho times g times v, but what does that mean? Conceptually, those things together represent the weight of the fluid that got pushed out of the way. So the weight of this fluid, it's probably an alcohol if it's got density less than water, is 100 newtons. That's the weight of the fluid that got pushed out of the way. And the question for us is, can we relate this back to the volume and density of the object that we have? So we know that this buoyant force has to be equal to the density of the fluid times g times the volume of the fluid displaced. We know the density of the fluid is 0.7. Or in our unit, 700. Specific gravity is 0.7. So we know little g. Volume of the fluid. If we know buoyancy and we know density and we know little g, we can find the volume of fluid that got pushed out of the way. Does that tell us anything about the volume of our object? Yeah. What does it tell us? They're equal? Why would the volume of the fluid and the volume of the object be equal?
It's submerged.
Good. It's submerged or immersed. Be careful here. If an object is fully immersed in a liquid, then you can say that the volume of the fluid and the volume of the object are the same. However, if your object is not completely surrounded by the fluid, you have to be careful. Let's say I had something that was, floating on the surface of water, right? And 40% of it were below the surface of the water. What would the relationship be between the volume of the object and the volume of the fluid?
0.4%.
The volume of the fluid displaced would be how much of the volume of the object? 0.4 of the volume of the object. Right? So do that check when you're doing fluid statics and you're dealing with these forces. See if the problem is telling you anything. They'll usually use words like it's completely surrounded or completely immersed. They might even say submerged. Those are all words that imply that this object is completely surrounded by the fluid. Look for words like floating, partially immersed, partially submerged, right? And then usually some sort of information about how much is in there, or sometimes you're looking for how much of it is sticking above the water or something like that. But here, we've got 100%. And since we have 100%, we can safely say that the volume of the fluid and the volume of the object is the same. So this lets us use this buoyant force, the density of our fluid, and little g to find out what the volume of our object is. It's going to be 100 divided by 700 times 9.8. Where did I get the 700 from? It's the specific gravity, 0.7, times the density of water. What's the density of water in physics? 1,000 kilograms per cubic meter. So that's where I got that. And when I do that calculation, I find that the volume of the object is 1.46 times 10 to the minus 2 cubic meters. So now I know the volume. That's one thing that they wanted me to find. And now I'm after the density of the object. Time to find out if this object is really made of gold or not, right? How am I going to find that density? What two things do I need? That was supposed to be an easy question. What's density? Mass over volume. Good. And I know the volume. Do I know the mass?
Yeah.
I do? What is it? It's not 300.
It's divided by G.
We need it in kilograms, right? In air, the weight of this object is 300 newtons. Divide by little g, and I've got a mass of 30.6 kilograms. Big object. And now when I go find the density, I take that mass, I divide by that volume that I found, then I get 2.1 times 10 to the 3 kilograms per cubic meter. I believe that might be goldish, but I am not sure. Key things to look for when you're doing Archimedes' principle, right? If they're talking about buoyancy or buoyant force, we're talking about fluid statics. In other words, the fluid isn't moving anywhere. It's holding things up. Typically, the objects are either suspended. They could be sinking, but generally, we're worried about situations where the net force on the object is 0. I want to do some more examples here, but I want to show you a video first. Balloons are happy objects, aren't they? Right? If you have a balloon, I like bubbles too. But if you have a balloon, things are happy. When you lose your balloon, it's very sad. When you wake up in the morning after the party and all the balloons are on the floor, it's also sad. But while you've got a balloon, it's happy. He doesn't look very happy. I think he was told not to be happy. Right? Let's see what's going on.
If we place this helium balloon inside a glass jar filled with air, it floats to the top. If we replace the air in the jar with helium, what will happen to the balloon?
Okay, why is the balloon floating? Helium is less dense than air. You could say lighter than air. That's fine, okay? But it's less dense than air. Is it just the helium we have to worry about?
And the rubber.
So there's the latex of the balloon as well. But even still, with the latex and the helium together, the average density, the overall density of that balloon is still less than the air surrounding it. You can tell because it's being lifted up, right? Pulling it up. So now, all the air inside of that chamber is going to be replaced by helium. So what's the balloon going to do? Is it going to stay at the top or is it going to sink to the bottom? Why sink to the bottom? Because we've got the latex, right? So overall, this balloon should have a density that's slightly more than helium. Because we've got to factor in the latex rubber. So let's see if that happens. Oh.
The balloon sinks to the bottom.
Okay, nothing earth-shattering so far.
If the jar is now lifted off the table, what will the balloon do?
Okay, they did not explain that one at all. Okay? I mean, obviously, if he takes the jar and goes, right? Balloon escapes. No, what he's going to do is he's going to slowly lift that jar up, okay? So that the balloon can stay more or less inside of it. But what is it going to do? Where is it going to be as he lifts that jar up? Towards the bottom? Like, how?
Lift it a little bit, right? Because there's still air coming from the outside trying to push it up.
Good, right? There's air at the bottom of that jar. Not in the jar, but sort of at the base, because the jar is full of helium, right? So there's air. And so in effect, what we have at the bottom of the jar is exactly the same thing we have as the surface of the ocean. There's a difference in density between two gases, and the balloon is going to be like a boat. What is it going to do? It's going to sink far enough, it's going to displace enough air to equal its own mass, its own weight. And so there's going to be a portion of that balloon that's down in the air, and then the rest of it's going to be up in the helium. You have any prediction as to how much of the balloon will be below the jar? Third, half, 3/4, 7/10, 9.378%. What? Almost none. So you think it's just going to be a little tiny bit? Anybody else believe anything differently? All right, let's see. Oh, don't smile.
It floats at the bottom of the jar.
About a quarter of its
If we
volume.
tip the jar to let the helium escape, the balloon floats back to the top.
Right here, the air can come back in, and so with the helium gone, floaty balloon again. So, you know, floating doesn't have to happen just in the ocean, right? Or water or anything else. Look for differences in densities. Well, let's just for a moment pretend that you are unsatisfied with your internet service provider.
You say that's not true?
And we're pretending now, right? And you decided that you're going to solve this problem for Fresno, and you are going to form a company that is going to provide high-speed internet access to the masses. We're going to really stick it to the man this time, right? And our brilliant plan for world domination begins with suspending high-gain antennas over Fresno, right? And so I went out and I looked up and just tried to find an industry standard for basically like the antenna masts that are on cell towers. Okay, so you got you got all the pokey bits that come off of the tower. How much do the pokey bits weigh? If you want to be able to pull off like 11 to 12 megabit per second transmission rates, okay, it's about a 4,000 kilogram mass, right? So what we need to do is we need to suspend approximately 4,000 kilograms below a balloon, high enough over Fresno so that everybody in the metropolitan area has line of sight to that balloon, but also not too low because we don't want any airplanes and stuff running into it. Does it sound like a crazy idea?
Yes.
Let's find out. So, what we're going to do is we are going to we're going to calculate what the amount of helium we initially need just to lift this 4,000 kilogram antenna off the ground. Okay? Right down here at ground level. We know that higher up where the air is less dense, we'll need more helium, but let's just find out initially if it's feasible just to kind of launch the balloon, right? Get it to float at ground level. So we've got to go calculate what this volume of helium is. And the analysis we're going to use, since the balloon will just simply be floating at ground level, is again, this is a fluid statics case. Buoyant force, we've got to draw a free body diagram and do the analysis of all the forces that are acting on the balloon. So I need a picture of our balloon. There it is. And what forces, what things are pushing or pulling on this balloon? So that's the force, the object being the Earth. Okay, what else? Oh, we've got a buoyant force holding the balloon up. Okay. Again, think about objects. Oh, the antenna itself, right? So this MG right here, what did you mean by that?
Everything.
Everything. You're just going to lump it all together. So there's the actual material of the balloon itself, right? the structure of the balloon. It's probably going to be a very thin, like polypropylene material or something, right? Okay. So there's that mass. There's gravity pulling down on the antenna. That's the 4,000 kilogram, the payload, right? But is that it? Is that the only thing the gravity pulls down on? Is there another object?
Helium?
The helium inside the balloon. Will the helium inside the balloon have weight? It has mass. Here's pulling on it. And the weight of that helium is something that the buoyant force is going to have to work against. So I'm going to add an additional one over here, mass of the helium times G, using the atomic symbol for helium there. So you might be sitting there going, oh my gosh, I'm so dead. There's no way I would have ever thought to include that. And you're half right. You're not dead, okay? Which you may never have occurred to you. But now that you've seen it, what are you going to remember to check? Are there other things? Okay. Do I need to worry about the weight of gases? Well, yeah, I guess I do, right? So put that down in your notes as something to just be aware of, right? I've asked you a lot to try to think of objects. What are all the objects that are pushing or pulling on this balloon, right? And that method of thinking about objects will help you far better than thinking about individual forces. All right. I'm pretty sure that's it. I can't think of any other objects. I'm not going to have any students hanging from the bottom of the balloon, hopefully. So I think that's about it, right? So I can go ahead now and write down my Newton's second law relationship. We want all these forces to add up to zero. Again, we're looking for kind of just that static case right at liftoff. We don't want it to be rising up. We can put more helium in it later if we want it to go up. Okay? So I'm going to make sure that my acceleration is zero. So mass times acceleration is zero. I'm left with the buoyant force minus the balloon's weight minus the antenna's weight minus the weight of the helium that's inside of the balloon. And check my directions. Did I do okay? Was I consistent? Have you noticed I've kind of stopped indicating my axes? Right? When you're doing statics, right, it can be important to indicate those axes, but it's actually more important to make sure that your statement shows what's going on in that picture. Buoyant force is acting one way. The other three are acting in the opposite direction. So my math needs to be consistent with that idea. I guess, to be clear, I'll call positive upwards. All right, well, how does this help me find the amount of helium I need? Where's the amount of helium hiding? In the buoyant force? In the volume of the balloon? Where's the volume of the balloon? It's in the buoyant force, isn't it? Because buoyant force is going to be density of what? Fluid displaced. What fluid is being pushed out of the way by the balloon? Air, right? And here's another kind of gotcha with buoyant forces. It's not the fluid in the balloon. It's the fluid that got pushed out of the way because of what's in the balloon. What's in the balloon is helium. But the helium is pushing or displacing air. And air is the fluid that's causing this buoyant force. All right? Little g. Oops. And then volume of the balloon. Right? That can't do much with the mass of the antenna. And I've got mass of the helium times g. So this is easy, right? I just solved that for volume of the balloon and I'm done. Nope. Volume of the helium is hiding somewhere else. It's hiding in plain sight. Well, volume of the balloon, right, and the volume of the helium will be the same. But there's something else here that depends on that amount of helium we have in the balloon. The mass of the helium, right? So, as we inflate and increase the volume of the balloon, we increase the mass of the helium in the balloon, don't we? So, is there a way for us to write the mass of that helium in terms of its total amount, the volume that we're putting in the balloon? Density. The density of helium is the mass of helium divided by the volume of helium. So the mass of the helium is going to be the density of helium times the volume of helium. And what can we say about the volume of helium and the volume of the balloon in this particular case? They're the same? Why are they the same? What can we say about the volume of the balloon and the volume of the helium? Why can we say it's the same? It's completely surrounded by air, right? It's completely submerged in air. It's immersed, 100% of its volume. So I'm going to go ahead and say volume of my helium is equal to the volume of my balloon. So now I can stick this in here. Density of air times G times volume balloon, mass of antenna times G minus, and now there's going to be density of helium times G times volume of balloon. I don't know why. I was always trained to write rho GV, right? Not rho VG. Gets easier to say rho GV than it is to say rho VG. It's all math to me. All right, got to solve this for volume of the balloon. So let's factor out the volume of the balloon. It's going to be what's something I can get rid of first? I'm in math mode now. I'm just trying to solve for something. Physics is going to go on hold. I can get rid of little g. Why can I get rid of little g? Because it's annoying. Because it's in all terms, right? Got to have a mathematical reason for doing it. And let's see, factor out the volume of the balloon. So I'm going to leave left density of air minus density of helium. And then I've got the mass of the antenna right there. Did I forget a term somewhere? Oh, I dropped my mass of the balloon, didn't I? There it is. It was up there at the beginning, and then it just didn't want to go along for the ride. So that G went away right there. And then I've got minus mass of the balloon. There we go. Move mass of air, antenna and mass of balloon over to the other side. They become positive. Divide by the common factor of the volume of the balloon. And now I have my answer. Okay. Stick the numbers in. Let's see. Mass of the antenna. The balloon antenna is 4,000. The balloon material itself is 6,000. Density of air they gave me 1.2, and the density of helium 0.179 gives me a grand total of 4.14 times 10 to the 3 cubic meters of helium. All right, let's talk about balloon material real quick. The high altitude balloons are made out of a material that is identical to this stuff. It's made out of trash bags, okay? This is a polyethylene plastic. It's really, really good at not tearing until you come along with a really, really sharp object, okay? In terms of like trying to get this to tear just by blunt forces, it really is quite resilient and really lightweight, okay? So that's a plus. 4,000 cubic meters approximately of helium required. That's a lot of sad clowns and dollar stores that don't have helium. But how much is that? This room is approximately 10 by 10 by 3 meters. So how many cubic meters of air are there in this room? 300. How big does our balloon have to be? about 14 times bigger than this room. That's a lot of balloons, isn't it? That's a lot of helium, isn't it?
Maybe.
Yeah. Until you realize that this has been done before. This is Felix Baumgartner. Felix Baumgartner was the first human being to break the speed of sound, to break the sound barrier in free fall. He had a spacesuit on, right? Okay. But in the parachute dive that he took from the quote-unquote edge of space, right? He broke the sound barrier on the way down, right? Pretty amazing. Jumped from approximately, I think it was 122 or 3,000 feet above the ground. Got there by riding a balloon, okay, with his capsule suspended underneath it. I believe it was a 6-hour trip in a very tiny room, okay, that basically consisted of life support, a window, and a porch, right? Porch being the important part because he had to be able to get out and jump, right? Okay. Here you can see there's the balloon as it's taking off. You can see how the balloon is not fully inflated, right there. Why don't they want to have the balloon fully inflated at launch? Its volume is going to increase as the density gets less and less, right? And he rode it up to the point where it hit the static equilibrium point, right? Where its effective density and the density of the surrounding air was the same. And then he jumped off and lived to tell the tale. I think one of the executives at Google, the high mucky mucks at Google, like 3 weeks later did the same thing and jumped from like 5,000 more feet. So technically they have the highest jump, but nobody remembers that person's name because they're not important, right?
Because they didn't come up with the idea.
They come, yeah, Felix Baumgartner. That's a good name to remember, right?
Did they use helium?
What's that?
Did they use helium?
Yeah. Yeah, it's a helium balloon. Okay? It's a waste. It is, but it's Red Bull. They do wasteful things. So, yeah. Right? But, I mean, just in terms of, like, the physiology of what happens to a human being when they're experiencing those kinds of forces, right? Because, like, his head broke the sound barrier before his feet did. And it threw him into a flat spin, which is a style of stall. And he had to train specifically to try to not black out when his body was spinning around his center of mass and all the blood, it was a red out actually, all the blood was rushing to either end of his body, right? So like, it was, I mean, and the suit that they had to build for him, and it had these special bladders in it that would, you know, puff up and try to force the blood back into his chest and keep it from rising into his, it's amazing. It's amazing. Just incredible.
His legs use prosthetics.
Yeah, you could do that too. But that wouldn't be nearly as fun. I have here a BBC News article. Broadband net goes stratospheric. Airships in the stratosphere beaming back broadband may seem like fantasy, but tests in Sweden have suggested it could become a reality within 3 to 5 years. Successful trial of the technology has been conducted by researchers. Trials using a 12,000 cubic meter balloon, flying at an altitude of around 24 kilometers for 9 hours. Provide the data ring, blah, 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 blah. Have you seen any balloons in Fresno? No? This article was written in October of 2005. Since then, this idea has gone pretty much nowhere. What happened between 2005 and now?
Stuff.
LTE. Okay, that's what happens, okay? Cellular towers back in 2005 were around, but now they're really around. Like, you can't go anywhere in town without basically seeing a cell tower. And it may not be the, like, prototypical big tower kind of thing, right? You got to look on the sides of buildings, right? What used to be on big towers are now being put on buildings, on fake trees, on all kinds of structures, right? To provide this telecommunications infrastructure. And it's kind of become sort of a moot point. Facebook and Google were testing balloons, both balloons and aircraft, solar-powered aircraft, that could stay up for like 3 months at a time to act as internet relays in India and Africa where they just don't have infrastructure. You go to Indonesia or to Southeast Asia, and they didn't have any infrastructure for any of this stuff. They went from basically not having telephones to having faster wireless communication than we do here in the United States. They just sort of skipped the whole copper landline thing and went straight to wireless communications. So there was a communications revolution that happened, and that's why we don't have very many balloons floating around. That and the fact that we actually are running low on helium. There's a national helium reserve, and it's been running out.
Well, if we quit blowing up balloons,
Yeah, that's kind of a problem.
or we could just do hydrogen balloons.
Yeah, there's an idea. Right? And the Hindenburg has, I think, scared people away from that.
That's the fun part.
And for those of you that are dissatisfied with your internet, I should probably not say things like this on YouTube. And I'm not promoting this company in any way, shape, or form, although full disclosure, I am a customer. Verizon has plans to roll out high-speed wireless internet access for $50 a month.
Good gesture.
Right? Unlimited. It's released in like San Francisco, Sacramento, and Los Angeles right now.
They just went to Fresno.
They
My
did?
brother works with Verizon. Or they're doing it
Changing
very,
my
very
internet
soon.
today. Right? Okay, because I'm sick of Comcast. And their data caps and all that kind of stuff. So, yeah, just realize that the future is kind of bright, although I can't believe I said that Verizon in the future is kind of bright at the same time. That we might have more competition. Also, 2 years ago, Fresno put out bids for municipal broadband, running fiber to everybody's houses. Okay? And I'm not sure what the status of that bid is, but the city of Fresno said, as part of the bid, you need to use the fiber optic network that is already in place. Does anybody know where the fiber optic network is in Fresno? There's one closer than you think to your house. Nope. What? Close. No. Traffic lights. When Fresno went through, starting about 10 years ago, and they started kind of revamping all the traffic light systems, okay?
Didn't do a very good job.
Well, actually, they did a really good job. Because every single traffic light in Fresno, except Southwest, sorry if you live in the Southwest, they have a bad infrastructure problem over there, now has fiber optic running to the light. And the reason they did that is because computers control the traffic flow, like on Herndon and along Blackstone and all that kind of stuff. And if you get into the right sort of group of traffic, you can actually go the entire length of Herndon without hitting a red light. Okay?
Almost never happens.
And then you're either driving too fast or too slow, because if you hit the speed limit almost perfectly, you're kind of guaranteed 80% of the time to get into one of those pockets.
This
Okay?
morning,
No, yeah, this morning is not going to happen. But believe it or not, Fresno's got a really good traffic system, especially with the lights being smart and changing with the presence of cars and all that kind of stuff. If you want to be frustrated, just go live in Los Angeles, right? Or San Francisco. The traffic system, the traffic light system there is abysmal. But we have a fiber optic network in Fresno, and the bid was for this company, whoever wins the bid, to just finish the fiber to the home, right? It's already there, you can use it. Traffic lights use like no bandwidth to communicate with each other, but we could have gigabit networking in Fresno, just running it from the local traffic. I'm ready to go down with my fiber to the traffic light, right? It's like a half mile from my house. I'll run a cable across the ground. I'm okay, right? I just want high-speed internet. The Sherpas on Everest have faster internet than I do. And more power to the Sherpas, right? But, come on. They can have high-speed internet at base camp on Everest. We can have it too. All right. Let's transition. Normally, I will start off with concept, right? To build a conceptual foundation, and then throw all the math at you. I'm going to reverse that for Bernoulli's principle and Bernoulli's equation. I'm going to do the math first. Get that out of the way. And then come back and fill in the conceptual holes. So, Daniel Bernoulli was an Italian natural philosopher, physicist, mathematician, depends, pick your poison. And he wrote down, well, he developed and then codified and wrote down a very interesting statement about fluids. Now, he was studying fluid dynamics, so this was fluids in motion. And for an ideal fluid, so we got to assume an ideal fluid. What is an ideal fluid? Well, it's physics fluid, but that doesn't mean it's massless. It has to have density, okay? However, we want to make sure that our fluid plays nice. So our fluid's viscosity is going to be very low. What's viscosity? What kind of fluids have lots of viscosity? Oil, honey, right? Corn syrup. Those are very viscous things. They have like an internal resistance to flow. They're very goopy. They're sticky, right? Water has a pretty low viscosity, but in our model here, we're going to just assume the viscosity of our fluid is 0. We're also going to assume that all the flows we talk about in any pipe or any system, they're all going to be what's called laminar flow. Laminar is a really fancy word for smooth. So we're not going to do turbulence. We're not going to do eddies. We're not going to do any of this weird stuff that can happen in fluids. We're just going to assume that our flows are nice and even. Fluid dynamics is a really, really hard math problem. I mean, fluid dynamics is like one of the reasons supercomputers were invented. Because when you start getting into fluid dynamics, you have to start tracking every molecule in the fluid, right? For trillions and trillions upon molecules, that's a lot of calculations. So we assume some simplicity so that we don't have to afford supercomputer calculations. So what did Bernoulli write down that was so significant? Okay, well, let me write it down, and then you tell me what you think it looks like. I'm going to go back and change this. Yeah, good question. There are both P's and rho's in that statement right there. Okay? So capital P's kind of on the fronts right here. Okay? Capital P's being what? Pressure. And then what looks like lowercase p's but really should be rho's, 4 of them. Those are what? Density. But this should look familiar. It looks like conservation of energy, doesn't it? I mean, not only does it have like a comparison between 2 points, but 1/2 rho v squared? What does that look like? It looks like kinetic energy, doesn't it? But it's not energy. What is it? What are the units of 1/2 rho v squared? Hint, what is it being added to? Pressure. It's pressure plus pressure plus, what's rho GH? Pressure, right? All 3 of these terms, when you add things together, they have to have the same units. So all 3 of these things are pressure terms. So one way you can say it's conservation of pressure, but it is actually conservation of energy, even though the energy units aren't there. It's all pressure units. The way that we are going to apply Bernoulli's equation is exactly the same way we applied conservation equations before, conservation of energy. We're going to pick 2 points, initial and final. We're going to pick 0. We're going to then compare what's going on at those 2 points in hopes for finding out some piece of unknown information. So the actual process here should be one that you were familiar with, right? We're just kind of giving it a different coat of paint and talking about pressures rather than energies. You'll often see this equation written as rho plus 1/2 rho v squared, or sorry, P plus 1/2 rho v squared plus rho GH equals a constant. That's how they'll often write it, like in textbooks on the internet. But since that constant is the same everywhere in an ideal fluid, you can just set the 2 equations equal to each other. So if you don't see it written exactly like this anywhere else, don't panic, right? I've eliminated a stupid conceptual thing that you don't really need to worry about and gotten straight to the chase. All right. There is a companionship equation that goes along with Bernoulli's equation. Okay? And it's called the equation of continuity. I've written it up there as area times velocity. And we need to be careful about what the units are in the equation of continuity. What are the units of area? Meters squared, right? What are the units of speed? Meters per second. So this is a meter squared times a meter per second. What was that? It's a meter cubed per second. Can you think of a different name for that? What is a meter cubed? It's a volume. And what's a second? It's time. This is a volume per time. What's going on here? Let's say we had a pipe that starts off with a really big cross-sectional area. Okay? So maybe it's a cylindrical pipe, right? Area 1 right there. And it narrows down to a smaller cross-sectional area. And a fluid, we'll use water, is flowing in that big section of the pipe. What happens to the water as it transitions from the big section to the small section? It speeds up. How do you know that?
Gotta make room somehow.
It's got to make room somehow. The equation of continuity tells you that your volume flow rate has to stay the same at all portions in your pipe. In other words, if 10 gallons per minute is flowing down one section of a pipe, irregardless of its shape or size, then 10 gallons per minute has to be flowing down a different section of the pipe. Otherwise, your pipe is like exploding or something, right? It's doing something that's not laminar, it's not nice. Leaking, right? We don't want any leaks going on, that kind of stuff. You've experienced this. You know how this works. Because at some point in your life, you had a garden hose. And the water was on. And you were watering something. And then a target came into view. Something that was just begging to be squirted. And so what did you do? You covered the end of the hose with your thumb to do what? Make it go further. Right? Okay? You changed the cross-sectional area of the end of the hose. And that caused the water to squirt out faster. So it went further. You'd even say, I bet, that you increased the pressure in the pipe. And you didn't. The only way to increase pressure in the pipe would be to close it off completely. Okay? But instead, you felt the force of the water trying to push your thumb off. Right? Okay? And you just assumed that that was the pressure increasing in the pipe. Technically, the pressure does increase a little bit because there's turbulence in the cartridge. But again, we're assuming ideal fluids. So, equation of continuity tells us what happens when pipes change sizes, when there's constrictions or anything else that's going on. Right? Bernoulli's equation governs fluid dynamics, the motion of fluids through pipes and changing heights, like going from one story to the second story or any of the other kind of things that fluids might do as they flow through pipes. So what I want to do is to demonstrate Bernoulli's equation and the equation of continuity is do a problem, do a particular example here of a siphon. So what I've brought with me is a clear container and a hose, right, and a bucket of water. Ugh. Right? And so, fill my bucket. What's a siphon do? What does it do?
Takes it from a low place to a high place.
Low place to a high place? Other way around.
It sucks.
It sucks. That's right. Siphons suck. Okay. Technically, they don't suck. We'll use it. All right. Or did you get what I'm sorry? Okay. All right, sort of. I've got my hose here, right? Okay. And how do I get this siphon started? How do I get water to flow out of the Out of the bucket. I got to suck on it, right?
Yeah.
Okay, right? Why do I have to suck on it?
Just concentration.
Nothing's happening right now, right? I got to get the water moving. Okay, well, this hose has been back for a while. Who knows what chemicals have come down it? And this is Fresno City's college water.
You'll be fine.
In the name of science.
In the name of science, put my body on the line. Oh, good. I didn't get any in my mouth. All right. So, oh, come on, flow, 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 flow. Fill the thing. Fill it. There we go. Non-turbulent flow. Okay. So, I've got a siphon, right? But I want you to watch what happens as I bring the tip of this hose up. Uh-oh. What happened? Stop. Why did it stop? My tip is higher than the surface of my water, but if I bring my hose right next to the side of the container, the level in my hose and the level in the container are exactly the same. So in order for the water to flow, what must there be? A height difference, right? Right now the end of my hose is too high. So let's see what happens if I take the end of my hose and I lower it down. No sucking required. Anybody need to go to the restroom? Okay. Now, you can do this. Now, if I introduce air back into the hose, right? Oh, and the floor's wet. Okay. It breaks the siphon, right? In order to start this again, I'd have to pull all the air out of the hose. But there's another way to start a siphon. Okay. So what I've done here is I have got water in the hose, right? So there's no more air. If I was very careful, there's no more air in this hose. We'll plug the end here, okay? Bring it over here. And now I should be able to let go, and water should start to flow. See how there's water everywhere in the system now, okay? And I've got a height difference between the water level in the container and the water level in my hose. Let's see what happens. Sure enough, right? Okay, oh, I had a little bit, oh, that was air. End popped up. Good, all right. Another thing I want you to notice, as the water falls, what's happening to its size of the stream? It's getting smaller, right? It's getting narrower as it falls. What you're seeing right there is the equation of continuity. What's happening as the water molecules fall?
They get faster.
They get faster. And if they're going faster, what has to happen to the cross-sectional area of the water stream?
Smaller.
It's got to get smaller. Equation of continuity. Now, don't answer out loud, but how many of you in an early state in the morning have stared at the stream coming out of your sink of water? And just like in that Zen moment, everything made sense, or you wondered why, oh, isn't that cool, right? Okay. And then maybe you were brushing your hair and you took the comb. Right? Okay. Humans are the same everywhere. All right. Later. I just don't want to die when I come back over here. All right. So let's analyze the siphon. This is fluid dynamics now, right? We're moving fluid from one point to another. There's height differences. We're not going to do area differences. In other words, my hose was the same area all the way along it. But let's see if we can figure out. Let's solve for the speed. How fast is the water coming out the end of the hose, right? For a given height difference. We know if it's at the, if the end of the tube is at the surface of the water, that it's going to be speed 0, right? But let's find out how fast it's going if we're like 10 centimeters below, 20 centimeters, right? Although, any height below that siphon. So, okay, I need a picture. So here's my container up there. It's full of water. I've got my hose. Kind of draw my hose maybe like this. Okay, and then there's water squirting out the end of my hose, and I've got to now kind of define points in my system, right? Bernoulli's equation wants me to pick one point and another point and compare those 2 points. Ideally, I want to know something about the pressures, the speeds, or the heights of the 2 points I'm going to pick. And since I want to find out how fast the water is flowing out the end of my hose, that better be one of the points I'm trying to analyze. Remember in conservation of energy, we always pick the final or initial to be the point where we wanted to find some piece of information? We do exactly the same thing here. So I'm going to call the bottom there, I'll call it point 2, I guess. Right? Or I'm going to call it my final. I don't care. 1 or 2, initial or final, doesn't matter. Okay? And so now I need another point. Where's another point in this fluid where I know pressure, speed, height, or at least I can make some guesses about it? At the top? When you say the top, do you mean the top of the hose? Ah, the surface of the water in the tank. Why not the bottom of the tank?
Submerged.
Well, it is submerged. But it didn't really seem to have much effect, did it? The tie we had was the water level at the top water level of the tank. Those are the things that wanted to be equal, right? If I drop the end of the hose below the surface of the water, that's when water began to flow. So there's something magic, there's something important about the top surface of that water. So I'm going to go ahead and pick that surface, and let's see what we know. All right, now that I've got the 2 points picked, I've got to pick a 0. Where do we put 0? The lowest point in the problem. So I'm going to put my 0 to be down there. Again, this is just like picking a 0 for gravitational potential energy, right? I've got to be able to measure my height somehow. I've got to reference him from some point. So I'm going to pick the lowest point in my problem. All right. Bernoulli's equation. Rho V1 squared plus rho G H1 equals pressure 2 plus 1/2 rho V2 squared plus rho G H2. Just like conservation of energy, are there things that I can get rid of? Like, are there 0 terms here? Height of 2. Where is H2? It's at 0 because that's where I put it. So that one I don't have to worry about. Okay, let's jump into the pressure. Pressure at point 1 versus the pressure at point 2. To be careful, I want the speed of the water as it exits the hose. So what is the pressure surrounding that fluid as it exits the hose? The same as it entered? In other words, the fluid coming out the end of the hose is surrounded by atmospheric pressure. What is the pressure on the fluid at point number 1? Atmospheric pressure. The pressures at point 1 and 2 are the same. I mean, there's a little bit of height difference, but in terms of the atmosphere, it's not going to make any difference, right? So the pressure at point 1 is 1 atmosphere. The pressure at point 2 is 1 atmosphere, and I'm crossing them out. Why am I crossing them out? They cancel each other out, right? They're the same on both sides. All right, there's one more simplification we are going to make. And it's about the speed of the water at point 1. It's not moving. It certainly is not moving with any speed that's even remotely like the water coming out the end of the hose. And in fact, for things like swimming pools that take days to drain, right, okay, that water level goes down very slowly compared to the speed of the water coming out the end of the hose. Engineers will often make this simplification, especially in systems like water towers, where the water is being fed in at the top at the same time as being taken out the bottom. The water level is basically not moving. You're not losing or gaining any water. So you can safely assume that the initial speed, right, or the speed at point 1 is close enough to 0 so as not to matter. If it isn't, like this system would not be a good system to do that. The water was actually going down at a measurable rate because the volume of this thing was so small. Okay? So in this particular case, I'd probably want to keep that. But I want to model what's going to happen in like your homework problems, right? Where they'll say a large body of water or a large tank is being siphoned off. That's a clue to you that you can say that the water, the surface of the water in there is not going anywhere, right? You can say the velocity at that point is going to be 0. So we'll go ahead and do that, which gets rid of that term right there. So what am I left with? Remember, we're trying to find out how fast the water is going when it exits. Oh, that's good. I've got that. Can I get rid of the rows?
Sure.
Oh, so it doesn't matter what the fluid is. I multiply by 2, and I take a square root. And what do I get? What is that?
Magic.
Final bowl.
The square root of 2h!
Physics.
Where have we seen that before?
Speed.
Yeah, how fast is something going when it falls through a height h? When there's no friction present. The answer is always square root of 2gh. I promise you, if you don't know the answer to one of your test questions next week, it's 2 square root of 2gh. Right? That's what you should guess. Because it's everywhere. All the time. Square root of 2gh is the answer. It's not 42. It's the square root of 2gh.
What a C.
What if 42 is what you did after you plugged it?
That's a different unit system. Okay? So, yeah. It shouldn't come as any surprise. What question did we ask? How fast was something going when it fell through a height h? Square root of 2gh. This is one of those moments in physics where physicists just kind of go, yeah, we're good. Right? Like, apply the same conceptual framework and get the same form of the answer, in this case, the exact answer. That tells us that our formulations are either so completely wrong that they're not worth doing, or they're so completely right that we've managed to find out one of the key ways that the universe works, namely conservation principles. So you then go test it, right? This is what makes it different from philosophy. You go actually do the experiment, right? To verify that this is what you get. You find out, yeah, that's what you get, right? And so physicists pat themselves on the back and say, we figured out how the universe works, okay? So let's take a moment to appreciate how far we've come, right? Okay, and all those different things. All right, let's take a look at the concept. So Bernoulli's equation has more surprises in store. Remember, it's this statement of pressure. It's supposed to be a 1 over there. P2, 1F rho V2 squared plus rho G H2. All right, sorry. When things get longer, I get messier handwriting. And so let's be simple here. Let's take let's take a pipe that is changing its shape, but not changing its height. In other words, sort of the very middle of the pipe is neither going up or down. So if we do that, we can safely ignore these two height terms. We can either set them equal to 0, or even if they're not equal to 0, they're the same as each other, and so therefore, right, it just wipes itself out. So I don't have to worry about those. What am I left with? So here's point 1. Here's point 2. And if I solve for... Let's solve for the difference in pressure, comparing P2 to P1. So basically, I moved P1 over to the right-hand side. It picks up a minus sign, right? Okay. And then I'm left with 1/2 rho v1 squared as being a positive thing and 1/2 rho v2 squared being a negative thing. What is this telling me? I've got a delta pressure there, right? A difference in pressure between the two sections of the pipe. And let's look at the right-hand side. Which of these velocities is bigger? 1 or 2? It's 2, isn't it? It's moving faster in the narrower section because of the equation of continuity. So when I look at the right-hand side, I'm taking a v that's small and squaring it and subtracting off a v squared that is bigger. So is this right-hand side going to be positive or negative? It's going to be negative, right? Which is telling me that the pressure difference between section 2 and section 1 is negative. So what can you tell me about the pressure in part 2 compared to part 1? It's less, it's smaller. The difference in pressures is negative. I'm comparing 2 to 1, which means that 2 must be smaller than 1. In other words, the pressure, the internal pressure of a fast-moving fluid is lower than when the fluid moves slowly. The faster a fluid goes, the lower its internal pressure. Is that true in your experience? No, because I know exactly what you're thinking of right now. Because you've been hit. You've been the target of the garden hose. Right? And when that water hits you, right, the faster the water is going, the more it hits, right? That right there is not Bernoulli's principle. It's not Bernoulli's equation. What that is right there is a Chapter 9 conservation of momentum problem. You've been impacted by a fluid. This is no longer fluid dynamics, right? This is trillions of little masses hitting you, right? What I'm talking about is when you have laminar flow inside of a pipe and the fluid moves faster, the pressure in that pipe actually drops. And this phenomenon is responsible for a number of things. Some examples I want to teach you right now. Bernoulli's principle, the extension, the conceptual extension of his equation, is responsible for cold legs in the shower, vascular flutter, perfume bottles working, airplanes being able to fly, and $1,000 fines on the freeway. What do all of those things have in common? They have this in common. Take 2 pieces of paper, okay? Hold them, you can try this one at home, okay? Hold them so that the pieces of paper are vertical to each other and separated by, I don't know, a couple centimeters, okay? And then bring them up so that you can, I put my thumbs together right here to kind of stabilize everything, right? We just want to hang them, right, 3 centimeters apart. And then take a big lungful of air, it's Fresno, so take your inhaler, and blow. What happened to the pieces of paper? Not moving my hands. They came together. Why did they come together?
Physics.
But why?
There was less pressure.
Why was there less pressure inside? Because that's where the fast-moving fluid was, right? That's where I was blowing between them. You could tell there was lower pressure inside because they came together, right? The pressure outside was bigger, the pressure inside was less, and it forced the pieces of paper together. That, right there, is Bernoulli's principle. What does it have to do with, pick one of my examples. Cold shower. Cold legs in the shower. Okay. So, don't raise your hand, okay? But just think in your head. There are two types of people in this world. There are people who take showers in the morning, people who take showers in the evening, right? Okay, let's just all pretend right now that you take a shower in the morning, okay? So you've woken up, you are in zombie mode, right? Because the higher brain functions have not yet begun. You are operating totally on your brain stem down, right? In terms of your neurological pattern. You stumble into the bathroom, right? Okay, and you turn on the shower. You have some method, whatever it is you perfected for morning showers, right? To be able to turn the water on without letting the cold water touch you, right? Maybe you are awake enough to realize that you can turn the water on and not be standing in the shower while you turn the water on, but that depends on your neural state, right? And as you're sitting there in the shower waiting for the water to heat up, the cold, clammy hand of death reaches out and grabs you in the leg. The shower curtain has attacked. Have you experienced this?
No.
Where you're in the shower and the shower curtain is coming in, right? And it's like taking up your personal space. Right? It's getting uncomfortable. Why is the shower curtain coming in? Where is the fast-moving fluid? It's inside the shower, right? You got the shower, and all the water coming down, it's pulling the air with it, and it drops the air pressure in the shower. High pressure outside, low pressure inside. Which way is the shower curtain going to go? It's going to go in. After you.
Is that only when it's cold?
No, it's hot too, but the shower curtain's always cold. Okay. So, how do you avoid this? Don't poke holes in your shower curtain.
The magnets on the.
Okay, little magnets, right? But even the magnets kind of don't help, right?
You put your
The magnets kind of just help it so that the water doesn't get out of the tub, right? But
Just plaster the curtain on the side of the
surface tension. There's a trick, right? You can kind of seal everything off, sort of. No, that doesn't work either. So hotels got tired of people screaming in the morning with shower curtains attacking them. This is a bathtub in cross section, by the way. Okay, and so what they did is they took the shower bar, the thing that holds the curtain up, right? And instead of having it be right over the edge of the shower, okay, they moved it out just a little bit. As a matter of fact, they do kind of a curve outwards, almost, okay? And what happens there is that the shower curtain is forced to I'm exaggerating here, but it's forced to hang at an angle now, right? Rather than straight up and down, right? It's hanging at an angle. And so that means that center mass of the shower curtain, right, is over there, and the shower curtain is constantly being pulled down and away from the shower stall. So if Bernoulli's principle, the pressure differential, tries to move it in, it's got to fight against that guy. What happens if it's a vertical shower curtain? It just moves, right? It doesn't care that gravity's holding it down, right? It's completely supported. So they can claim that their showers are bigger. They're not. They didn't try and change the size of the tub. They can't because that's specified by building code, okay? But they can claim that their showers are bigger because there's more psychological space in the shower now, right? Because the shower curtain isn't coming into attack. Or you can do what I did, which was when I became a homeowner, I made sure all of my showers had doors. Right? No shower curtains. Screaming in my house, but no shower curtains. All right. So what's another example I told you about?
Speeding tickets.
The what?
Speeding tickets.
Speeding ticket. The $1,000 fine on the freeway. All right. So what is that one about? Study group here on campus, right? You've been studying physics for hours. Probably only been minutes, but it feels like hours. And everybody needs a break. And everybody says, oh, let's go to In-N-Out Burger, right? You say, okay, well, you know what? I'll go get it, right? Just give me your order, give me your money, and I'll go get it, right? So you get in your car, you drive to In-N-Out Burger, get everybody's orders, you're back in the car, you're driving back to City College, right? And I apologize to all the vegetarians in the room right now, okay? But can you smell smell of it now, Bert?
No.
I haven't had lots many.
The French fries, the double. Right, again, right, okay. Now, nobody will know if you take just one French fry. I mean, nobody gave you gas money, right? So you're perfectly, like, it's okay to take one French fry. It is sitting right there on the passenger seat, right? So, and nobody can eat just one. You gotta make sure that the other French fries, you gotta have a representative sample from all the French fry packages, right? Okay, to make sure that they're all good, right? And pretty soon, before you know it, you've torn through 4 French fries, 3 double doubles, and a couple of root beers, right? And now you don't feel so good. You're driving along the freeway, right? You've got, of course, you know, it's fast food, so you get an 1/8 pound of a burger and 5 pounds of paper, right? And so you're hot, you're getting the sweats from the grease and the oil of the French fries, and so you roll down the window, and what happens?
Stuff blows out.
All the paper goes whoop right out the window. $1,000 right there. Why is that $1,000? That's the fine you get for littering on the freeway, right? Okay. Why did the stuff that was sitting there all of a sudden decide to get up and leave? Where's the fast-moving fluid?
Outside.
Outside the car. Where's the not moving fluid?
Inside.
Inside the car. You're like, well, I'm going pretty hot, right? Yeah, but the air inside the car relative to the car isn't moving. The air outside the car is moving relative to the car. The lower pressure is outside,
And it wants to go high.
and it wants to go there. Okay? Hopefully it's heavy enough that it doesn't poop out the window, right? Okay? Don't ever pick up balloons for your kid's party and drive around with the windows open.
Did you do that?
I didn't. But certain unnamed people in my family that have a driver's license and isn't a child did. Right? And she came home saying, I lost a few balloons. You had the windows open? She's like, yeah. Why? It was hot. Tasty. Wasn't hot enough. Sit down, honey. We'll talk about Bernoulli's principle. All right. Airplanes. How do airplanes fly?
Change one, right?
Carefully. No, airplanes fly because they have wings that are shaped funny. This is kind of how an airplane wing is shaped in cross-section. The front of the plane is over here to the right, back of the plane is over here to the left. Airstream comes in, has to divide over the wing. Part of it has to go over the top, part of it has to go under the bottom. What can you tell me about the air that has to go over the top of the wing?
Faster.
It's got to go faster. Why does it have to go faster? There's more surface area there. A longer distance for that air to travel. And so it has to move faster to meet the air on the back trailing edge of the wing. The air on the bottom didn't have to go as fast. Where is the faster moving fluid? On the top. Where's the slower moving fluid? On the bottom. Which way is the pressure going to be? Up. Actually, this is mostly a lie. But it's a good one. Okay? There's actually a lot more going on here in terms of physics. Collisions of air molecules with the wings frame and all kinds of other things, right? But as an oversimplification, it's not a terrible one, right? The lifting force that airplanes experience comes from a combination of the cross-sectional area of their wings and the speed. Our airplanes don't go flat through the air, right? Okay? We have to get them moving fast in order to generate lift so that they can fly. Very different from the way that a bird does. I'm not a very pleasant person to travel with in an airplane because I insist on the window seat, and because that's where all the cool stuff is happening. And when the plane is taking off, right? I can't decide which is more exciting. My nose pressed against the window, watching everything that's going on outside the airplane, and the wings and everything. It's all so much physics going on out there, right? Engineering, or wanting to lecture the person next to me in the middle seat about everything that's going on outside that window. It's like Bernoulli's principle applied right there. I'm always so that you get to sit, you get to feel the acceleration, the whole acceleration, right? And it takes off, and there's that moment when the airplane can't decide if it wants to fly, right? And take off, and it passes, and then the pilot pulls up just a little bit too soon, and the plane goes, okay, we're gonna fly, right? Okay, and then it's so exciting. And the best part. There's at least 30 minutes before that fasten seatbelt sign goes off, so I had a captive audience. What else? Other examples? You remember any of the ones I mentioned? I don't.
So can you flip that upside down and have downforce?
In order for an airplane to fly upside down, you do have to have a special wing shape. All airplanes can fly upside down for a limited amount of time. But the ones that are designed to fly upside down actually have symmetrical wings. And they have a different shape for flying up. Most airplanes can't fly up down for any length of time because their fuel tanks cannot be inverted. In other words, the gas only flows in one direction. So if you have an inverted fuel tank and you're careful, you can get any airplane to fly upside down.
I think there was like a movie that said like a pilot did that for like a few seconds to save the passengers based off of a true story. So how mad were you about that movie? I think it had like Denzel Washington in it.
Oh, then it was awesome. The only thing I think I've ever seen Denzel Washington in is, remember the Titans? Otherwise, I don't know. Yeah, no, don't fly airplanes upside down. It's not a good idea. Unless they're designed to, in which case, knock yourself out. Don't knock yourself out in an airplane. It's not a good idea. All right, I think. Did we make it? I think we made it. Yep, we made it. So, what do you have to do now? Chapter 13 homework by Saturday, but ideally by tonight. Because when is your chapter 14 homework due? Next Wednesday, right? Because of the test that's happening, right? So, you're welcome to stay, right? And get help on chapter 13 probably, right? Or if you want to get started on chapter 14, I can get you computers if you want to check out a computer. If you turn this into a little graph section, you're welcome to go. I'm not going to force you to stay, right? But the time is yours. I will be here until the next lab section comes in which case I'm going to repeat all the same thing I do. If I don't see you, a good day. If you're staying, let me know what I can do to help you. All right?
Wow, it's not bad.